Alright, so we've looked at the work done by a spring. Let's look at the potential energy that we can store in a spring. This is going to allow us, once again, with all the different types of potential energy and kinetic energy, we'll be able to use the conservation of energy to solve a lot of these problems. And if you can use the conservation of energy, I recommend it. That's what I'm building up to right now. We're going over different types of potential energy. We're going to go over what the difference between conservative and non-conservative forces are, and we're going to look at the relationship between the forces and potential energy. After that, we'll start looking at the conservation of energy and how we can use it to solve problems in one of my favorite fashions. It's one of my favorite tools in the toolbox. We can deal with friction. We'll see what happens. Causes a change in internal energy. I'll go over that. But let's look back at the work done by a spring real quick. If you remember, flip into my book real quick. The work done by a spring we calculated as the integral of Hooke's law, the spring force, dotted into the displacement from some x1 to x2. And what we ended up with when we integrated was a minus 1/2 kx final squared minus 1/2 kx initial squared. And you'll often see this swapped around with the minus sign flipped so that we end up with 1/2 kx initial squared minus 1/2 kx final squared. Now, using potential energy in the spring is going to make things a lot easier, so just bear with me. What we see, though, is that if we're measuring from an equilibrium position, and I'm going to go over all these cases in just a second. If we're measuring from some equilibrium position, say x is equal to 0, then we can say the potential due to a spring, or the energy stored in a spring, is equal just to 1/2 kx squared, where x is the amount stretched or compressed. Either way, remember the force is the same, just in an opposite direction. Amount stretched or compressed. Alright, so that's one we need to know. And this is always a positive term. It's never negative, okay? The energy stored in a spring is going to be positive. We're going to look at the total energy of a system before and after. So energy before is equal to the energy after. And we're just going to put in what's the spring stretch on the left-hand side in its initial configuration, and what's the spring stretch on the right-hand side. And it's going to be positive in either case. We don't have to look at the work done by the spring to solve the problem using conservation of energy. So this is a very powerful tool. And I'm going to go over some scenarios, but before I do, I want to go ahead and say something twice. When we look at the stretch of a spring, that it does not matter which direction it is stretched in. So if I wanted to know, I'll do this problem probably, but there's some collar that's allowed to slide down and it's attached to a spring on a wall. Now we could say that the stretch is equal to 0 initially, and then as it goes down to some position 2 from position 1, it's going to have to stretch. And we could figure out what the speed is right here. I'll show you how to do that. But a lot of people get confused because the force is now being applied up at a different direction. Do we have to do the dot product and the integral to figure out the work done? No, you don't, because we can just put in how much was it stretched initially on the left-hand side of our equation, and how much is it stretched finally on the right-hand side. So in this case, we'd have to do a little trigonometry to figure out how much it was stretched. So I'll do this problem for you. It's from my dynamics book, actually. But good problem involving using the conservation of energy. Okay, so let's look at some different scenarios of a spring. Let's say we got some springs here. Whoops. Each one of these is going to represent a wall with a mass on it attached to a spring. And let's draw that spring. Alright, I'm going to draw the equilibrium position at the front of the spring. Let's use a different color. So here is our equilibrium position. We're going to say this is equal to x is equal to 0. And that is our equilibrium position. At this point, delta x is equal to 0, therefore 1/2 kx squared is also equal to 0. If the spring is not being stretched or compressed, it has no potential energy, no stored energy. Now, if I decided to compress this spring to something like this, and it now moved over some delta x, then we can say the the energy stored in the spring, or the potential energy, is 1/2 k delta x squared. This energy wants to push back in this direction, just like the spring force, but what we'll find out is that if we release it, it can turn back into kinetic energy, right? If I release this, I'll do the scenario in a second, but as it passes right back through the equilibrium point, it's going to have a maximum kinetic energy. I'll do that whole scenario in just a second. Let's do the one last. What if we stretched it instead? Dang it. So this is equilibrium, this is compressed, and this is stretched. So now the block is out here, and the spring is doing work on the block in this case. Okay, we might have to do force to apply a force to compress the spring, but when it's released, the spring will do energy on the mass of the block and give it some 1/2 mv squared. That's kinetic energy, right? So in this case down here, we're going to stretch it. And we're going to stretch it some distance. If this was our equilibrium position, it's now stretched some delta x. This case above was a minus delta x if we compressed it. This is a positive delta x. Turns out that doesn't matter, right? We just have the potential in the spring is equal to a 1/2 k delta x squared. It has the same amount of energy. So if we'll call this delta x prime, and this is just delta x right here. If the magnitude of delta x, or the amount that we compressed it, is equal to the magnitude of x prime, or the amount that we stretched it, then we can say that the potential energy in the spring is the same. We have stored the same amount of energy in the spring. Okay, now what if I took a mass I connected it to a spring, and let's say that our equilibrium position is right here. Alright, that means we stretched it, right? So we got a spring here, and we've stretched it some delta x out to the right. Now let's release it. What's going to happen? Well, it's going to accelerate. Figuring out what the acceleration at any given point is actually kind of tricky. Take my dynamics class and we'll figure that out. But we have a mass here, we have a force being applied, and it's going to accelerate. We know that from Newton's second law. Using the using energy theorems, we can say that it's going to turn some of this spring potential energy into kinetic energy, which is the 1/2 mv squared. So basically, it's turning the spring energy into a speed, a velocity. We can always extract that as long as we know the mass. So, as it's out in its most stretched position right here, what does the energy look like? I made a little, we got bar charts in our book. If it's at its most stretched, if I had potential energy and kinetic energy and then maybe the total energy, well, it's going to be all potential energy. It's at rest right here. We haven't released it yet, so the kinetic energy is 0. 1/2 mv squared is 0. And then the total energy is going to be exactly equal to whatever the potential energy is at its maximum stretch, whatever we just stretched it at. As we release this, as it passes through the equilibrium point, so let's do right before equilibrium. So right before it goes through the equilibrium point, our energy is going to change. We will have some potential energy still because, let me scroll back up a little. We're saying maybe instead of being right here, we're now right here. We still have some delta x. It's still stretched, therefore we still have some potential energy. But now we have motion too, so there could be some kinetic energy. And if you add these two together, you will get your total, what we call mechanical energy. And it should be equal to the total mechanical energy when we stretched it initially. However much energy was stored in the spring is now equal to the total of these two, potential energy and kinetic energy. Okay, now as it passes through the equilibrium point, what's going to happen? Well, we will see, let's go back to our picture. That means, let's draw a new picture, actually. So, it is now passing through the equilibrium point, exactly through what we're calling x is equal to 0, and this is also the spring's relaxed state. It takes a force to stretch a spring, so if you let it relax, that would be a 0 displacement, and we can say that's its relaxed state. So, bottom line right there, our delta x is now equal to 0. There's no displacement in the spring. So if we look at the potential energy, it's 0. We have none. As soon as it goes a second or a little instant of position further to the left, we're going to get a little bit of potential energy. But as we go through the equilibrium position, we have 0 potential energy in the spring. What we will get is a maximum of our kinetic energy, meaning the speed maximizes through the equilibrium point. And this is a no friction scenario. We'll deal with friction when I talk about the difference between conservative and non-conservative forces. Then I'll talk about the conservation of energy, and then I'll talk about what we do with the non-conservative forces, because conservation energy doesn't like them, but we can still throw them in the equation and solve problems that method. So what we find out is that in this case, energy is conserved, and the total energy in the system is equal to whatever the kinetic energy is. And I could let this spring, or this mass, oscillate even further until it compressed the spring an equal amount to how much it was stretched. So, in other words, before we had, wrong color, before this was our equilibrium position, we had stretched the spring out some delta x. Well, this has enough kinetic energy to turn back into potential energy to squish the spring the same exact distance delta x, just in the opposite direction. So what we get is something that looks like this. And there's our compressed spring. So now, if it is completely compressed, meaning all of the energy is now back stored in the spring, that means the kinetic energy is 0, or the velocity is 0. This is its turnaround point, and this is where it sped up through the equilibrium point, and then it slowed down, came to a stop, and it's going to speed back up through the equilibrium point through its maximum velocity at the equilibrium point. And then it'll keep oscillating in simple harmonic motion unless we have some outside force like friction or something to remove energy from the system. So our total energy is whatever we have stored in that spring again. Alright, so that gets me to the fact that we can say the total mechanical energy, so mechanical energy, meaning dealing with motion and stuff, the total mechanical energy is equal to that potential energy plus the kinetic energy. And you'll see potential energy as U, sometimes as V, and you'll see kinetic energy sometimes as T. If we look at any of my ME 242 textbooks, you'll see the conservation energy is not written as potential energy plus kinetic energy initially is equal to potential energy final plus kinetic energy final. We'll call it T1 plus V1 is equal to T2 plus V2. Same thing. Just be prepared to see lots of changes of variables in your academic career. As you change textbooks, as you get more advanced, they're going to start having to use more variables. And honestly, it's cheaper to write T1, V1. Okay, so this went over a lot of the energy bar charts. If you have any questions about that, just ask me some questions. But basically, we're transferring energy from one form to another. I'll go over one little part of an energy bar chart. What if we had, got a ruler here, let's use it. Let's say we have a book on a flat surface. So this is some mass, and there's our book. Okay, if this has some initial velocity, we'll call it V naught, and it's on a frictional surface, and we have some frictional force pointed to the back. What we can see is initially, if maybe it was given an initial velocity and then it enters the surface. So maybe we hit a hockey puck onto a surface, then it started experiencing friction, and then friction slowed it down as it traveled to the right. So think of it like that maybe. So the book is sliding, but friction is slowing it down. If we look at its initial state, where it is sliding only, and look at our energy bars, it's all kinetic energy. It's all 1/2 mv squared. Our potential energy is 0. In this case, we're not going to have potential energy. There's no spring, there's no gravity, but we can look at what's called internal energy. And this will introduce what's happening with friction. So we haven't looked at the work done by friction, but we can still calculate that. The work by friction friction is just a force. We can do F dotted into dr, or we can say it's equal to mu times the normal force, that's our frictional force, and times whatever our displacement is, delta x. This is not conservative. We will introduce this shortly, but what I want to introduce is one aspect of what non-conservative means is that we're not transferring back and forth between potential energy and kinetic energy and back to potential energy. We can't do that. Instead, we're giving what's called internal energy. We're adding heat to the system. So initially this has no internal energy. It's just got a velocity or kinetic energy, 1/2 mv squared. And so we can say the total energy is equal to whatever that kinetic energy is. The total energy of, in this case, the system, which is just the book. If we look at it a couple moments later when it's still sliding but not stopped, then the kinetic energy is going to drop down a little bit depending on how far it traveled. And that's because this friction has turned into heat or internal energy. I didn't mean to make these equal, they could be different. But what we see is that the total energy is going to remain constant. So our total energy is the same that we had from our initial state. Okay, now what about when it's completely stopped? Friction made this stop completely. Well, if it has stopped completely, that means our kinetic energy is equal to 0. Our 1/2 mv squared, since v is 0, now goes to 0. The reason it stopped is because the work done by friction. So the internal energy, or essentially basically the temperature change. It's not that simple. You'll learn in thermodynamics, but the temperature has gone up and it's now internal energy. So we have a rise in internal energy due to the friction. And we'll find out that that equals the total energy of the system. And all three of these total energies are the same. Now, with something like internal energy, we cannot transfer this back into, we cannot turn this back into a 1/2 mv squared or a mgh, right? This is our kinetic energy, and this is our potential energy due to gravity. We can also not turn it into a 1/2 kx squared, the energy due to a spring. It's basically lost. Unless you have some mechanism like an engine to turn that heat back into motion somehow, it's lost to us in terms of mechanical energy. Remember, the mechanical energy, or the total energy in the system mechanically, is that potential energy plus the kinetic energy. Alright, next I'll talk about conservative versus non-conservative forces. And that'll get us into this whole friction thing. And how we're going to deal with it when we do the conservation of energy. Alright, thanks y'all.